Boom, boom, boom. That should be good. There we go. Okay. Is this too? No, I think it should be. Hello everyone. Okay, so that is fine. Got this chat over there and this one over here. And I just need to, okay, perfect. Okay, hey folks. So today what we're gonna do, I'm still on the Google Meet. I tried to go on Riverside, but it didn't work out. Like tried to plug my stuff on the on their app, and it just couldn't find my channel. So we're still gonna go with this crappy Google Meet / LoRA flow. My face will not be on the little LoRA thing, but I think that's gonna be enough. And after that, I'm gonna be joined by Bidipta, I think I pronounced his name properly, which is the main author of the article we're gonna review today, which is Evolution Strategy at the Hyperscale. So it's another ES type of paper. I fucking love these. Like these are absolutely amazing. I like them. I like how the that's it. Like how they're kind of taking the same type of problem we've been looking at, and then just using another methodology completely that shouldn't work, but still kind of work. This one, what is cool with their paper is that they actually try to do pre-training on some weird that, well, that's not weird, sorry for that. It's not traditional like decoder only feed forward type of LM architecture. Yeah, so a lot of nice oddities in this article. So I have a whole bunch of questions for my guy once he is gonna come in about like 30 minutes. But if you have more, don't hesitate to put it into the comments and on the chat, and I'll just ask them out over there. And I promise we're gonna get there, right? We're gonna get a better setup at some point. And also, if you have any question related to deep learning, machine learning, whatever it is, that is not directly related to paper, it doesn't matter. You can also post them there, and I'll stop the stream and just answer that straight up. So this is the paper, right? Evolution Strategy at the Hyperscale. Pretty nice one. A bit more mathematical than the other ones that I've reviewed, especially that like they're pretty good on the proof side. So if you're more math inclined, you have a whole proof of like whatever they're claiming about their ES metric gradient deviation, and the fact that like it is converging to a full rank type of story. So that's our guy. He's gonna come pretty soon. But the main claim on this paper are that you can use ES, right, and kind of a LoRA style of workflow in order to pre-train, right, model, in order to like post-train, fine-tune them, right, or in order to do like straight up RL from scratch on them. It works surprisingly well, and it is efficient, which is always a problem with the evolution strategy. They're very like, can't say it, like memory angry. So in this case, they are able to kind of palliate to that, and they were testing this with billions of parameters. This is kind of related to another paper I'm gonna like talk a bit about, but that's the idea. So they have Eggroll, which is their kind of algorithm. We're gonna dive a bit into it, but basically how it works is that you have these like low rank perturbation that you're doing, right, and you are doing a whole lot of them, right, a whole lot of these low rank perturbation to create that noise that is kind of Gaussian what's it, like a Gaussian shaped. Then you put them into your nice little fitness evaluation. You weight average them, and what you get out is literally like a full rank update matrix, right? And all of this can be done pretty efficiently, to the point that like it is really close to, in the pre-training case, just batch inference, right? So a lot of cool optimization that they've been doing in this. So this is the idea, and because you're doing this low rank kind of thingy over there, right? You get much more speed up than if you were to do it directly on this kind of bigger matrix. The rank need to be like smaller, but here you can do it on rank 1, and it's still kind of performing quite well. There's three main stuff here. Eggroll does not compromise the performance of ES in tabula rasa RL setting, despite being faster. So it's both faster and it's actually performant. It's competitive with gRPO for LM reasoning. Kind of the same result that we've seen with that other evolution strategy paper with Yulu. And Eggroll enables stable pre-training of nonlinear recurrent language model. This one is a bit intense, right? They made a model that is called Egg, and it only work in like in like purely integer data type. There's no activation function because there's already a nonlinearity over there. Pretty wild stuff, but I have a lot of questions about it. So that's the method, right? Pretty like intuitive and simple, I would say, but some nice result. You said once, we have a question here, once check out LoRA paper. Oh, I think I've never seen that LoRA paper. Oh, is this one you're talking about? 13,000 of concurrent LoRA adapter, pre-training, then fine-tuned paradigm is commonly adapted. Okay, so yeah, it kind of look a bit similar in terms of how it's shaped. Nice. I'll take a look at it, definitely. We have a question here. I love sharing about our AI taking to start a YouTube channel. I'm wondering if you can share about the income ad sponsor. I know that shouldn't be motivation, but I want to have... Yeah, don't do it for that because I'm making barely anything. There's a question about like if this shit is worth it in terms of revenue generation. It is not worth it. Like, yeah, I'm gonna be real here, right? The way you make money usually on YouTube is if like you have a population that can pay for stuff, and if you have enough reach toward this population, this will make the ads revenue go up. In this case, you guys are a niche, right? Of a niche. So we're not talking. Yeah, it's really niche down, right? So ads revenue is kind of abysmal. Sponsor, however, work great, right? And like the issue if you're doing like educational stuff with sponsors is that, I mean, at some point, like you're gonna do what? You're gonna jam the sponsor in an education segment. It's a bit weird. It's a fine line to kind of go. So you have to really find like sponsors that work super well with the kind of vibe that you're going for. Scrimba for me is like a good sponsor that I kind of always go back with. I also had the sponsorship with Tildra. So these guys that make the board, I got sponsored from them. So yeah, you have to find something, a shape that kind of makes sense for you. But like the sponsorship usually are calculated by the amount of views that you're getting. So, dude, I think if you want to make an AI education channel, you just have to be careful, right? And I think the best shape is more like the other stuff outside of this that can happen, which in my case is like some consulting client, right? Some cool people I can meet, that type of stuff. Like a lot of the thing around like the consulting business that I was starting up. The reason that it worked out is because people were looking at this channel and then they looked at it was pretty legit and I knew my stuff. So you should also view it maybe in this light. Hope it helped. If I can earn 1K a month, I would be happy at least to afford to pay for video editing and do only. Oh, I do all my video editing myself. This is why it sucks. Sorry, man. I don't think you're gonna be making enough to pay for anybody. Hey, Joyce, how are you doing? Hope you're having a fantastic day, whatever the world you are. Hey, you messaged me on LinkedIn today. Perfect, man. I'll get back to you mostly later today. Cool, folks. So let's get to it. Well, first off, guys, thank you very much, right? All of the little sponsors that I have here that are sponsoring this channel, you're literally paying for all the expense, especially on the software side. So yeah, really appreciate it. And I also appreciate the fact that like you guys decide to support this. A lot of you are doing like some really cool things also. Don't hesitate to message me. I'm super happy to chat with all of you. Okay, so in terms of the related content, related research for this paper, one thing that you should definitely check out is ES for LM fine tuning, right, with Yulu. It was super a good chat we had with him, and it's kind of adjacent to this, right? In their case, they are mainly working on the post-training aspect, right? In this case, it's like it's heavy on the pre-training, but they did it in a different way, right? They did it during the rollout, which technically speaking, you can combine into method. So you should definitely check this interview that we did with him, about an hour. And we also did another one where we actually literally went through his whole paper. Check this out. And in all of these, like kind of new genre of like ES, like a methodology, they're all kind of based in this thing, right? So, wait, is this one? No, it's not this one. It's this one, yeah. Evolution strategy as a scalable alternative to reinforcement learning. And this is Ilya that published it in 2017, right? Remember, like when OpenAI was doing like some weird StarCraft stuff, right? Yeah, man, this is it. Like most of them are referring this because basically what they tried was to do ES on RL, and they just show that like, wow, ES works super well. And then I think they called it Open ES or something like that. So anyway, there's an algorithm in there, and then it's benchmarked against their thing here. But there's a lot of inspiration from like the overall methodology. So if you want to kind of get catch up about like where this thing is based, it's kind of based on this one. So this is what Ilya saw. It's that ES is actually useful. So there's a bunch of important concepts, right? This paper, honestly, like there's paper that you can read in a day and you're like, yeah, I get it. This one I would tell you to kind of take a whole week to kind of study it, because it's coupling a lot of different concepts into one, and it's mixing it in a very interesting way, right? So the first thing that you kind of need to understand is it's kind of about LoRA, but it's also not about LoRA, right? So low rank, what's even the name of LoRA? I don't remember. Oh boy, I'm getting better, guys. I just came back from being sick. So low rank adaptation. Wow, why did I miss that? Yeah. So it's about low rank adaptation, right? But also not that much, because it is doing a whole bunch of it in order to kind of get a full rank thing at the end, right? So it's using that during the ES to be able to do that. There's like a lot about the Gaussian matrix distribution here, which are used to do the sampling of the errors, and then this is coupled with the ES type of methodology. So you kind of need to be familiar with like these three things, right? And it's doing in the proofs, it's doing whole lot of gymnastic in order to prove that like whatever they're doing with this and that, like make use of the nice property of having Gaussian Gaussian metric distribution in the noise. So that's it. And then once you combine all of this, you get this nice stuff. Plus, right? It is not done. Plus, the GPU optimization they've been doing, right? So it makes the algorithm a bit more weird, but it's absolutely needed. And it was the same thing in the other paper. Where is it? Yeah, here, right? They did this whole gymnastic here in order to make it even better. So a lot of moving parts, right? Yeah, and then the experiments are even more intense. There's 3 of them. They're very short, right? But there's a lot of engineering that had to happen. They literally made their own pre-training model. Yeah, take a solid week, right? A solid week would be useful here. So that's the idea. We can get into the main difference, right? So it's not a LM paper because there's other stuff that they're working on, right? And even when they're using LM, it's not a typical type of LM, right? But there's still a LLM, a large language model with billions of parameters. It's just that like it's not a Quen or like a DeepSeek or a Llama. It's what's it called? I never saw that one before. It is the RWKV paper, so the Goose with expressive dynamic state evolution. Yeah, so it's this one that they're fine-tuning. It still has 1.5 billion parameters. They were able to fine-tune that thing. Yeah. So there's a whole bunch of paper that like did like some LoRa on sort of ES directly on the LoRa's, right? Matrices. So they're doing like supervised fine tuning setting in this. The one thing they're showing is that like in these work usually there is not a large population size, and in their work they show that like the large population size. So a large population means that like the amount of these perturbation that you're doing, right? So this will tell you where to go, technically speaking, right? So you see here, right? At the beginning you're here, and then you're doing all of these perturbation in all these direction, and then this tells you like, hey, buddy, you should maybe move here, right? So generation 2, you're doing the same thing, but like a bit more spread out in this direction, and it's kind of moving like that, right? So what they're saying is that now this is in 2D, it's not too bad, right? But in our case, there's like billions of parameters, right? So there's billions of direction things could go. So in this specific case, you have to be able to do it in this multi-dimensional space, and you need to kind of like have a lot of what's it like population test of all of these parameter direction. So they are saying that you need to have actually a large population size. So yeah, there are other elements of the CMA ES, and so their claim here is that there's most of them are on small population size, yeah. So but it's kind of related to Q, but also not that much. So this is the Yulu paper. There's a few things, right, that kind of align together before we get into the actual Eggroll algorithm. First, low-rank approximation, right? They defined it properly. They said that this thing is frozen, and then you have here your A and your B that correspond to that shape over there, right? And these are trainable, right? So this is what you get over here. And if you make R small enough, then it's worth it. If it's too big, it's like you're not getting that much. But if the rank here is smaller, you're doing this properly, right? So then you can do the LoRa stuff. Then you have to add the fact that like they're using Gaussian matrix distribution. We're gonna take a pause here. We have a question. Quick question: how do you find the time to do this alongside a full-time job? A good question, right? That's a pretty good question. But like the actual stuff with me is that I'm always learning things, right? Like I'm always like reading a paper, like coding something, or so like I'm never not learning. It's not like I am an employee in a big tech and whatever, and I have a manager and stuff. I'm kind of an entrepreneur, right? I had a business that I co-founded like 7 years ago. I quit that business, and now it's running on its own, right? And now I'm making another one, and like right now it's mostly consulting stuff that I'm doing. But I hire people, and then I work on project and that sort of stuff. Like it's not like I have literally in a day I need to like do these tasks, right? I can think creatively and figure ways of like having other people do the task, me myself doing the task at night, or the fact that like I know all of these things and I'm learning constantly, make me a bit better at like well, first getting the contract and also getting the task done, right? Yeah, so I don't know if it's answer your question, Akrita, but I'm always learning stuff, and I'm like more on the entrepreneur side than employee in whatever business, right? I make my own rules. Okay, so Gaussian matrix distribution. The noise is gonna be sample from this, right? And it's like a generalization of the multivariate Gaussian distribution. So this stuff, right? It's a generalization of this in like over vector space, right? So this is what we're using over here, and we can measure the distance between matrix using that. So keep that in mind because it will pop off just here because we're doing a Gaussian matrix evolution strategy, right? So you take that and then we're defining the evolution strategy. So it has this shape, right? So you have your objective here, right? And it's gonna be on the parameter space. So this is achieved by learning the set of parameter theta to maximize the expected thickness Fz under a population distribution. So this is the population distribution. And then we take the derivative of this, right? And this gives us our gradient. But this gradient is not like an actual, I don't say it like, it's a natural gradient, right? Because it comes from this quantity here, which is like kind of our gradient thingy, is known as the score function, which avoid taking gradient directly through the fitness function in equation 1. So this, we're not taking the gradient from this, we're taking like this more natural gradient. And then we're jamming stochastic gradient set here on that directly, right? Nothing fancy here, right? It's just straight up SGD, and we have that kind of gradient that we're using. So we're updating the parameter a bit like this. So like in a nutshell, right? You jiggle the parameters a bit, right? A few times in different direction, and then you take that into account to have like a score function, and then this score function will tell you like roughly speaking where you should be moving, and then you're gonna update in this direction just a tiny bit the parameters, right? This is useful when like you have your parameter here, right? And you need to do a whole bunch of stuff, right? And that is maybe long, and then you have a score function that says like, hey, it's good, or like, oh no, it's bad, right? Like if this reminds you of like reinforcement learning for LM fine tuning, it's because it's kind of, I think there's some about that made this a good method to revisit. So it's not taking this into account much, right? It's taking this into account, and it's jiggling this to get like a lot of these trajectory, right? A lot of these little cloud. You can get a whole bunch of them that are working in all various direction, right? And they're going to give you all of this different result, and at the end you take the average of these, and then you're able to decide like where to go with the score function. So that's the idea, and then you're not doing this over like just one or two like parameters. Like you're gonna do this on like a Gaussian matrix kind of noise. So we're using the Gaussian matrix policy here, and the ES objective is changed to this, right? So the ES policy is that stuff, right? We're gonna change it to that, right? So you have the parameter of the Gaussian now being introduced here, over there, right? And then E over here is like the, that's it, like the, it comes from, wait a second. It comes from the evolution strategy stuff that we're doing. It's like the error, right? So this is what we're introducing into the mix, and then we have our fitness function in there. And then we calculate the matrix gradient of this stuff like that, right? So it gives us this form over here with these parameters, and that's what we're gonna work with. This is not even Eggroll yet. It's just like the basis that we have for it. So here we see from equation 4 that Gaussian matrix C is meant to optimize the objective G of mu by generating search matrix this from a standard matrix normal distribution around the parameter matrix here. This is important because we're going to sample from these Gaussian matrix, right? Like we're going to use that to sample, and it will save us a whole bunch of time, right? A key benefit of natural gradient is that it takes into account local geometry of the underlying parameter space when updating the search distribution, making the update invariant to the choice of parameterization. So it's kind of robust, right? So that's that. So this is the setup. This is what we're working with. And then we have the actual Eggroll, right? The actual flow of the Eggroll is huge, right? Like, well, actually not that huge. Well, it's actually huge because like it goes like this, and it explained like all of the decision that they made. But even in the how's it, like the appendix, you're gonna see like they went into all of the details about like the little steps that they had to take, and the justification for their stuff. So if you want to dig into this, feel free to do it. In our case, we're gonna take a few shortcuts. Any questions so far about anything that I just said? Like I said, if this is your first exposure to this stuff, you're gonna need a week to hopefully with like our man Bidipta that will come in a few minutes, we'll be able to short that time a bit. Okay, actually he's technically should be coming in 5 minutes. I'm gonna tell him just like give me 12 more minutes. That should be good. All right, getting there. So Eggroll, right? The algorithm is like this, right? So in this case, now we're gonna include the low rank evolution strategy into the flow, right? So the low rank approximation A, B transpose must be carefully integrated into the Gaussian matrix. There's a specific way they're integrated it, but at the end you get this, right? So you keep the variance proper by having this term over here, right? And then the actual what's it, like gradients look like this. So this is the full formula, right, that we have. And then the scoring function that you need for that, like there's a z parameter that I kind of brushed over, but there's an epsilon that you're adding over here. And then this is a hyperparameter that you can kind of tweak. But anyway, right, you get this gradient and then you get this core function over here that include all of the stuff that we've discussed. So here, this is the z with your little epsilon. So there's a very specific mathematical reasoning why you need that, but you have that. And then you have this core function, right? And then this core function is kind of not arbitrary, but you can change it, right? So in their case, they decide to like have the update rule be this stuff, right? And they swapped it a bit in various direction, but they found that this was the most stable. So you sample A here, you sample your B here. Remember, like these are like Gaussian matrix distribution. You get your low rank perturbation over there, right? With this kind of form that we've looked a bit over here, right? And then like your update will be like that. It looks a bit different, right? Than like, sorry. It looked a bit different than what we were saying over here. Here that was super duper simple, right? But it's because we're doing a multi-color estimation of the stuff, right? So you have multiple worker here that are working in parallel. So you're gonna do that motion of like multiple one of them at the same time, right? With different kind of sampling, and then you're gonna create the average of them once you shove the fitness function that we just discussed. So you got these over there, right? That are using like the Gaussian kind of parameters that come from this stuff, right? And then by doing this, you're taking the weighted average, and this is how you can kind of reconstruct like a full rank without having to actually do a full rank one. And then they show that it converges to a full rank. So that's that, right? The algorithm is this. So you're doing it in 2 steps, right, for optimization purposes. So your first step, you're doing a lot of recomputation, which is fine, right? So here the E, you're going to reconstruct it twice. The reason for that is that you don't want it to keep too much in memory, right? You want to actually get, you want to like let the memory is kind of a bottleneck in this specific case in ES for the pre-training, post-training, fine-tuning of models. So you have to be careful of that. So they're doing very careful reconstruction, and they're being wasteful in some cases because they have to recompute stuff, but it's for a good reason, right? So at each of the worker, the N ones, in parallel you do all of this, so it's like very GPU friendly over there, right? And you take your A, your E, and then you calculate the F. Now you have all of that, right? And then because they all share like the scalar fitness function here with other worker, you're able to run this, reconstruct all of the E's, and then create the average, I'd say it like use over here, right? To do your weighted average. And then this is one time step, right? And you continue doing this again and again. So you're gonna go at the same time, you stop, you do another run of that, you reconstruct E, and then you just run again and again per time step. And this is actually very, very performant. So we can actually look at the three main experiment, and after that we're going to be able to chat with our guy. We have some question. Hey Yasin, I just wanted to share some information. I'm currently building an AI for a crypto market system. I'm sure it will work. Best of luck, buddy. You can DM me about that. Hi Yasin, how do you transition from 9 to 7 to 5 job to your entrepreneurial journey? Did you build the audience first? How would you do it if you were starting over? Actually, I dropped out of my PhD to do the first business that I've done. So I was YOLO from the start, guys. I would not recommend it for everybody, right? Hey, hi Yasin, how are you doing? Do you make like these live weekly every Friday? Yeah, usually it's weekly, and I need to get better at like having a schedule, but we're running these weekly. And next week we're gonna look at how's it called? The blog post that just came out with the guy that is like 300 times faster than the TRM and cheaper. It's still getting developed, this thing. We'll see in the weekend what's up with that. Okay, so the first pre-training the first experiment that they wanted to do, they actually made a model called Egg, right? And it looked like this. It has a very particular shape. But basically, like it's a Ant8 data type model. So there's no float, right? It's all integer, right? And they made it so that it fit Eggroll. So all integer, it's nonlinear RNN, right? It's not like the normal transformer type of stuff. It's nonlinear RNN, and because like it doesn't matter, like for evolution strategy, it doesn't matter what happened in the middle, right? So we don't care. We're not doing backpropagation through time. We have the parameter here, the output here. So because we have this shape, you can actually make it an RNN, and it's fine. You can train it efficiently. And then they actually removed all activation function. I don't know why. This one I found it pretty funny. Yeah. Anyway, so like this is a setup. They have like a particularity about how it's set up, but the end result is that when you use OpenES, right, versus Eggroll, the speed is absolutely insane, right? Here you're very close to just pure like a batch inference type of setup, right? It's really performant, and more performant than PP over here. And the population size kind of matter for the performance, right? So you see, as you have more population, like the performance is better and better at the specific task that they were working with. They did a few more ablation here, right, on the actual population size need. And they kind of what's it like checked with the amount of data that like the different population were having, right? And like when it's balanced over there, you see that still like you need to have a higher population than like the higher the population, the better the performance. But like you don't have to like have a different sequence for each of the member of the population. You can reuse the same thing, kind of, right? And you get performance. But like the less population you have, the more it can diverge, and you need to have like different sequence for each. But if you have like a different population, a lot of different population, you can reuse mostly the same sequence. So this is good. So like pre-training, check mark, guys. We're doing great. RL pre-training, right? Actually, also doing super good. They're comparing this to GRPO. No, this is OpenES, right? It's PPO. What if? Given their small network size, we can use. Oh yeah, it's OpenES that they're using over there, and it's much faster than OpenES, right? So, but like now we're not looking at the wall clock speed. We're looking at the steps. And long story short, on the Pendulum, the Brax, Craftax, Jumanji, Kinetics, and Navix, we get some good performance. And in total here, we have Eggroll is competitive with OpenES on 7 out of 16. It underperformed 2 out of 16 and outperformed 7 out of 16. So it's like actually overall better across different environment. But it doesn't account the speed up when compared to using OpenES, right? So like it is supposed to be much faster, so technically you can run more step. Yeah, we postulate that the reason for this performance increase is that large network are difficult to optimize for OpenES and lend themselves well to low rank update. Was interesting thing that they said over here. I'm gonna ask them a question about that. So that's what's going on. So pre-training, RL pre-training check, RL fine-tuning, LM fine-tuning here with the RWKV architecture. Also is going super well, right? They're comparing this to GRPO, right? It's 1.5 billion parameters, so it's a lot of parameters. It's not just like a small model. Well, it's small compared to the gigantic one that we have, but like it's not just a small model. And you see here the performance, but one thing that I found that interesting is in here they're not using steps, they're using relative wall clock time hours, right? And we know that this one is faster than GRPO, so I don't know if there's more step here or stuff, so we have to ask a question here. But Eggroll overall better across different instantiation, and there's a bit less of a jiggle over here. GRPO some run were better than other runs, so there's a bit of a spread. Yeah, and overall here with this is for the countdown task, so this is for the GSM 8K. They're pretty similar, but like Eggroll is a bit better. A countdown task was a specific task that also is appearing on the other paper that I've showed last time on evolution strategy. So if you want to look at the difference, you should also check this one. Yeah, so yeah, overall, like LM fine-tuning also it's working. What I've liked if they will use other model also, just so we see like the difference. I think they are actively working on this stuff, but that's roughly speaking what's going on in this paper. Whew! Yo guys, how long I did that in 30 minutes? Quite crazy. I just distill all of this in your brains. But you should definitely read the paper. Our guy will come. We have a few questions. YOLO from the start is bossy. Yeah, I'm like that. Can you cover some physics informed ML paper for upscaling problem? I should dive into physics informed ML paper. Actually, I have a client that might benefit from a physics inspired type of network. Okay, I'm gonna let him in. You can jump in. Bus, we are ready. So wait a second. Do I have the? Yeah, it should be good to go. Hey, how are you doing? Can you hear me? Yeah. We're doing great. Yes, I think everybody can hear you. Everybody. Can you hear our man over here? I think we should be good. There's a bit of a lag. Yes. Good. Oh, wait. They're saying no. Ah, shit. Wait. Is this better, guys?
Can you guys hear me?
It's on my side. It's not on your side. Because of my riggedy setup. Sorry, man. Like, now it's better. Yeah. Okay, perfect. Good. We got it. Okay, for the next interviews, I swear we're gonna actually get a proper setup. So thank you for being here, man. Thank you for putting up with my rescheduling because I was sick, but we finally got it. I really liked the paper, honestly. It was good. It was very mathematically thorough, to be honest. It was nice to see, especially since like it's like language modeling and NLP. I don't know. I feel like sometimes we kind of veer on the sense of like, yeah, if it work, it work. But in your case, you were very rigorous, which I really like. Can you tell us a bit about your background and like where your research interests lie at the moment? I know you're doing like you're in grad school right now with like in 2 different labs. Just tell us a bit more about this story.
Yeah, so I did my undergrad at Stanford, and I'm currently at the second year of my PhD program at Oxford. Yeah, co-advised by Jacob Forrester and Shimon Weitzen. So that's the Flare and Whirl labs, the final 2 co-authors of this paper. Yeah, it's kind of tricky to answer like what my interests are. It's kind of a bit of everything. But yeah, I guess like one of my core interests is just like as compute scales up, how can we leverage methods that can like best leverage this compute, especially like large parallel compute, and also just like trying out wild things and seeing what works.
Yeah, it's good. And like, what's wilder than like evolution strategy?
So
Yeah.
I guess my first love has been multi-agent reinforcement learning.
Yeah, I saw that.
High
Yeah.
school, back in high school, I started a project where we tried to do like multi-agent RL. This is like the old TensorFlow 2.0 days when you had to like use the tape and stuff like that. It's yeah, I still get nightmares about those. But yeah, so yeah, multi-agent RL, just like seeing like a bunch of different agents learning to cooperate together to compete with each other. I think one of my big fascinations is just like artificial life, trying to see how like life can emerge from itself, and of course, evolution lends itself nicely to that. Also, a bunch of other things: world models, sequence models, transformer alternatives, and yeah, just a bunch of little things here and there. A little bit of robotics, and yeah, LLMs are now big. So multi-agent RL plus LLMs is another thing I've been interested in. So
There's just so much. Honestly, like there's just so much interesting direction these
yeah,
days. It's very dynamic. If you just look at like the model output and the benchmark, you might not see all of this, but no, yeah, like there's just so much going on. We just reviewed your paper. Like I actually reviewed it in and I tried to compact it out in 30 minutes. Can you walk us through on your own word like the core intuition that led to this and like what did you see and like roughly speaking how would you summarize this research?
yeah. So I think the big takeaway from this research is if you can do batch inference, you can now do training. Like that's the one thing I want people to take out of like this work as a whole. And it doesn't like as long as you can like evaluate how good a model is, and you can do this batched LoRa inference, you can now just do training. And it doesn't. It can be literally anything. It could be the pre-training objective. It could be like a model that you can't do inference on, or sorry, you can't do training on super well. So like non-linear RNNs, or like you can just go like completely hog wild with it. And yeah, so I think that's like the core takeaway from this. And I think the key insight about like why Eggroll works relative to OpenES and these other methods is like OpenES kind of takes a very like principled stance on like, okay, we want to have like this Gaussian matrix perturbation, whereas we say, well, do we need to? Like, how can we like make it a structured matrix so that it's more computationally efficient? And we see, yes, we actually can. And this can give us a lot of computational tricks at basically no performance loss in terms of a per step level, and just like drastic speed ups. And like, yeah, rank 1 LoRa is kind of the easiest thing we could try out in the context of GPUs. In other compute paradigms, maybe it could be something different, but at least for GPUs and like TPUs and like most of these modern like large scale systems, Eggroll is quite effective.
I like that this what's it like a sorry there's like a bunch of kids yelling here so it's all fine. Uh, the smallest one just learned that he can just yell. So he's just yelling and he's like reinforcing the fact that he can just yell. So these days this is what's happening. But that being said, like there's what's it like I like the fact that we're especially in academia now in all of these research lab we're kind of moving out from the fact that like we're just looking at the theory, right, and like looking at like theoretically what should happen, to having these very impactful research that are kind of hardware, not like a hardware informed, right? Because like this thing will go somewhere, right? And we're gonna need to train these things. So the fact that like we're optimizing for that, create these nice research where like it is much more efficient, and you can like push the thing a bit farther and see stuff that you would not see before. I really like the graph where you're like at 83% speed up. That was kind of insane. But before we go into this in more detail, like where and why did you get the idea of using like the LoRA rank matrix perturbation? I know there's another paper that did that, but it did ES directly on it. But you used it in their whole mix. So where does the idea came from?
Yeah, so it's a bit of an interesting story. So over the summer, the UK government just gave us like a bunch of GPU hours. They're like, okay, we see that you love this like a bunch of cool work. We're going to give you like 100,000 H100 hours, or sorry, 400,000 H100 hours, and you have 3 months to use it. And I'm like, okay, that's cool. Like in academia, we're super compute limited. We would love to get more resources. And then a couple of weeks passed by, and it dawned on me like, oh my God, how are you going to use 400,000 H100 hours? We have a lot of creative people who are doing like a bunch of language model stuff, but it's also like a little bit tricky to get started. So I was like, okay, we have so much compute, and we don't want to be known as like the lab that dropped the ball on like this gigantic opportunity. So I was like, okay, what's the most insane thing we can do? So the most insane thing I could think of at the time, and like I was not like super aware of like all the prior like LLM ES work, is like, okay, we can take like a 7 billion parameter model and then just do evolution on it. And that's like the largest model we did on this paper currently. We did RWKV up to 7B models. So like, I was like, okay, so let's just do evolution on this directly. And then I was thinking a little bit more, I was like, maybe that's a little bit too insane, right? Especially if we want to have like evolution, if we want to exploit like large population sizes. This comes a little bit from my background in like, I took a class at Stanford on like GPU programming. It's called CS149. It's like the best class I've ever taken. And basically they're talking about this idea of arithmetic intensity, which is about how many flops or how many bytes do you need to load in per arithmetic operation. So for instance, like if you just use each flop like only, or each byte only once, like you just multiply these two and then accumulate, right? That has very poor arithmetic intensity. What you'd prefer is something in which you reuse the same matrix multiple times. So if you do naive ES, the issue is that you have this batched matrix multiplication. So you have like this m by n matrix, and then you have this like b times, like a batch of b different matrices. But if you like expand out how this would actually work in terms of the matrix multiplication, it means that you're using every byte only once, which is super, super, super bad, right? And that's where all the speed up comes from, or like the slowdown of OpenES comes from relative to PPO. Right. So what I was thinking is, okay, well, what if instead of just doing like an arbitrary like full rank perturbation, what if we just do like a low rank perturbation, right? Like we see that low rank has been relatively efficient, and also shouldn't matter too much, right? Because this is just like a random jiggle, right? If we structure the jiggle, it doesn't matter like that much. And also like if we're able to kind of average over like a bunch of rank 1 updates, this will still become full rank, as long as these are kind of independent of each other, right? So that was kind of the intuition. I prototyped it in like a day because JAX is just amazing, and also because RWKV is amazing. And yeah, I didn't need to like worry about energy transformer, PyTorch, CUDA, all that other stuff. Just like JAX, RWKV, and I just prototyped it in a day. I wrote to my supervisors like, hey, I think I have like a breakthrough. This could like change everything. And yeah, here we are.
I love it. I love like how it started from like for like the that much compute being dropped on you, and you're like, what can I do with it? Which is also very interesting because it shows that like yes, it's fun to be kind of constrained because then you can think out of the box. But when you really relax this constraint once in a while, you can get like these wild ideas and these breakthrough pretty consistently, right? Just a quick question about the name Eggroll. Like, did you think about it and then like you because I know that the other of your models and architecture has a specific name. Did you design the name and then figure out the abbreviation? How did it work?
Yeah, so it's a bit of both. So when I first came up with the method, I was like, okay, we have evolution. So the original name was actually evolution group relative because I was using the GRPO or Dr. GRPO style normalization. It was like, okay, evolution, GR, and then low rank learning. And it's like, okay, EGRL. And then I was like, okay. But then eventually we changed the acronym around because like the group relative stuff is actually like not super important to like, it's not fundamental to our method. But like we acronym, we had to like iterate on like what the acronym meant. But after like the first week, I was like, okay, we're dead set on Eggroll. And
Yeah, this is so cool, man. Like, but I think the naming is important. Like
yes.
to some extent, you see that in the history of like just artificial intelligence in general, right? Once they got the understanding that like naming stuff properly, from a marketing standpoint, will like help get the direction to scale a bit more. This is what you get.
I think also
Um,
the fact that eggroll is really good as a verb as well. Like throughout like the last few weeks, we're just like,
sure.
oh yeah, just eggroll it, or like, oh yeah, I'm eggrolling this thing right now. It's like it just flows very nicely.
Oh, this is nice. Also, this is the second paper of kind of dive deeper on it on evolution strategy with like LMs. What do you think like made now a good time to kind of like revisit like this sort of because like we've had this this thought that like you could do ES instead of RL from like 2017. Like it's not something new, but now it seems to be more prevalent and there's multiple paper about it. Like what's up on this front?
Yeah, so I would attribute this to the fact that GRPO exists, right? And we're doing like these long reasoning style models. Because if you look at the OpenAI ES paper, they had like a couple stipulations about when does evolution work better, right? And one of them was like super long, like trajectory lengths, because you would need to kind of backprop through it, or like you need to like do a lot of bootstrapping for long trajectories. So that's why RL is kind of bad for that. But ES doesn't care because it just like doesn't matter like how you take it. It's just the endpoints, right? So that's one thing. Another thing is like our value functions. Is a learnable value function like does it exist for your problem setting? And what we're seeing, like just empirically by the fact that GRPO has replaced PPO, like the only difference really between GRPO and PPO is the lack of a learned value function, right? So it's like, okay, well, if you're giving up on value functions, then you might as well give up on RL and just go straight to evolution, right? Yeah, I think that's like the main reason, and that's probably the reason why we've been thinking about evolution as like an alternative to LLM reasoning. And that's kind of where I started with for Eggroll. And then I was like, okay, we can kill RL. And I think like the results from our paper and also the prior evolution strategies works kind of shows that like evolution strategies can kill RL reasoning fine tuning. But we wanted to go bigger and say, okay, let's kill backprop. And let's see how far we can go in terms of killing backprop. And yeah, that's kind of where we're at.
It's kind of crazy that we went from like, hey, let's kind of RLHF learn a full. There's a specific big model over here that will learn this stuff. To like, well, actually, like the model could be its own value a thing to just like you don't even need any of this. You don't even need gradient descent. Okay, I love it. There's a section in the paper that said something very interesting. It says, here we consider the limitation solution to applying ES at significant scale beyond the small network and population size of these prior work with a broad focus on policy learning. Why the focus on policy learning specifically?
Yeah, so I think in the context of that paragraph, we were specifically talking about like all the places where ES is already applicable because backprop just doesn't make sense, right? So there's a lot of work on what do you call it, opponent shaping, meta learning, and all these places are areas where like ES is already like dominant, and like we see it already works. We would expect Eggroll to also work in those. So like there's a couple of people in our lab who are trying to run experiments with that. just for like the additional efficiency gains, but like we want to see, okay, in areas where RL has, or where ES is currently not dominating, what can we do? And are there new things that Eggroll could unlock? So like we just want to keep kind of the most general setting where like we know that ES isn't currently like the best or like the go-to method for everything. And that's the main reason why we focused on it in this paper.
That makes a lot of sense. And it brings me. I'm sorry. I think I'm.
Sorry,
muted.
I can't hear you.
No, it's me. Sorry, because I'm muting two mics at the same time. This makes a lot of sense and brings me to the other ES paper. But there's one that is doing ES directly on LoRA matrix, right? It's like the derivative-free optimization for low-rank adaptation in large language model. How does your model? I know you didn't benchmark this, but like how roughly would it compare to like doing it directly on the LoRA versus like using LoRA internally?
Yeah. So it's a little bit. Yeah, we'll definitely add this benchmark because I think this is a very important comparison. We kind of learned about this paper kind of late into the paper's release, so that's why like we didn't fully benchmark it. But I think it's like a reasonable thing to try out. But I do want to say that like it's basically it would behave similarly to the trade-offs between like LoRA on RL versus like full RL. So like according to the Thinking Machines post, we would expect this LoRA ES, like directly doing LoRA on the ES on the LoRA matrices. We would expect that to probably do decently in RL or like RL fine tuning. But for pre-training, the issue is that even if you're doing like ES on LoRA matrices, you're still trapped in that like low rank perturbation, right? Which is like, like people see that it's okay for a lot of RL specifically for like reasoning fine tuning, but for like pre-training from scratch or like even SFT, we see that that's not sufficient. So we would expect the same trade-offs that you would see from backprop-based methods to also apply to ES. Whereas Eggroll, even though it has like a low rank perturbation, the update is still full rank.
Right.
That's
right.
So like we're much more similar to regular ES than we are to LoRA.
True. Because like this is what I was saying, that like it's not actually LoRA. It's like the LoRA like a shape is within the ES versus like you're using ES on LoRA. So the flow is a bit different, but I think like like benchmarking it just to show the difference will be. I think we're gonna find something interesting there. Which bring me to another kind of general question about the paper, because in it, because I've read the other ones, right? And in this one, there's a very high emphasis on the pre-training, which I found very interesting. Because like you would think that like pre-training with ES makes absolutely, well, the naive version of it kind of makes no sense as you scale toward more parameters. And I was talking to Joseph Suarez about that, and it was like, it doesn't make any sense. But with the changes that you made now, it kind of makes sense. But you mentioned something that was super interesting. You said that a large population size are necessary for pre-training performance, indicating that zeroth order optimization method will be unsuitable for pre-training. And can you just, I know that like in Appendix E, there is some data about that, but can you just put some color a bit around that statement?
Yeah. So I guess, so like during the original parts of like the development of this project, we started with like the RL, the LMRL stuff, reasoning. That's kind of our first part, and then we did like kind of the standard RL experiments, because this is like what we would expect from an ES paper. And then finally, I was like, okay, YOLO, let's just try pre-training just for the fun of it. And then we found some like interesting scaling laws, so we were like, okay, this could be something that we introduce as like a sign of life, more so than like a current practical method. Though we are trying to see like how far we can take this, and like Dimitri on Twitter has been like just going on fire in terms of like getting this to like actually be like quite practical. But yeah, so the point that we wanted to make here is that like we see very clear scaling curves in terms of like basically if you multiply the population size by 0.8, or sorry, you multiply the population size by 8, you get like a 0.4 drop with the same number of steps or update steps, which is very interesting because typically with SGD, you do not like just increasing your batch size for a small model like saturates very quickly. And especially with SGD, Atom helps ease this somewhat, but like even then, like just naively scaling up your batch size does not help. So we were very surprised to see this, but it kind of does align with what people see from ES. But the more important point is that like at a very small scale, like if you have a very small population size of like 64, 1,000, that like prior works have gone up to, like 1,000 is like almost inconceivably large for like prior ES works. But like if you just stopped at that, you would see, okay, there's no point. It's completely useless.
Right.
That's what we see in the appendix, right? It's like, this is completely unusable and there's no hope of it like doing anything. But what if you just scale it up and just make it bigger, right? If you just bigger and bigger, then like sometime you're eventually going to find something that works. And this is not possible with prior ES works because of the inefficiency of batch matrix multiplication, right? But because Eggroll, we're able to like scale this up to like hundreds of thousands of population size. And like in our newer experiments that haven't been added to this paper yet, we can get up to millions and like tens of millions.
Oh, jeez. Whoa. Okay. Nice.
Yeah.
I love this stuff, man. This is so cool. You said something about Adam being able to help on this front, and I know that you used a stochastic gradient descent, I think in the vanilla kind of version. Are you planning on like testing out other optimizer here, or you think it's not gonna be that useful?
Yeah. So I think so yeah, a lot of prior ES work has used Adam. It's a little bit trickier to integrate this to the pure pre-training, just because of like, I want to make sure that the entire code base never uses any floating point ever. If you relax that a little bit, you're able to get Adam to work. And yeah, we see that it's actually quite effective already in terms of helping out if you release this like arbitrary int restriction. But yeah, we do think that like it's very important to like develop optimizers specifically for Eggroll or like evolution strategies in general.
Okay.
Like, so much of our intuition about like what is good, like what are the issues with just naive stochastic gradient descent, have been influenced by backprop, right? And these backprop-based methods, like Adam, is designed to like overcome the oddities of SGD, and we see that like SGD is very easy to overfit and stuff like that. Whereas evolution has its own set of quirks, and Eggroll specifically, like there's still so much we don't know, and this is such an open area. Like I'm just hoping that someone like does optimization work on Eggroll, and if they don't, I will. Right? I mean, I will do it regardless. But and then there's also like, this is just throwing something out there, right? But like evolution has been super good for like meta learning, which is like a lot of people have meta learned reinforcement learning algorithms. So like, how do we improve Adam for reinforcement learning? There's a lot of work on that. It would be super cool to do something like that for Eggroll, where we use Eggroll to improve Eggroll and have like a better optimizer than what Adam would give us with Eggroll. But yeah, optimizer is important.
That makes super a lot of sense. If anybody in the chat want to work on this, guys, reach out. I had another question about the Eggroll algorithm, and I think there's a few questions in the chat about that too. Just nothing mathematical here, but like, what's your rough hunch of why the method work with like rank equal to 1? I know that like as you increase the rank, like it's working better. But like rank 1, what do you think it works?
Yeah. So the intuition, which we're still working on formalizing, because I think this is actually theoretically grounded, but you know, the other members of the team are like working on actually formalizing it, is the fact that like essentially for each parameter is like decorrelated with all other parameters, right? So like if you think about evolution, and you're always moving the same two parameters either both up or you're moving them both down, you don't know like which parameter should you be moving up or down. If like suppose you move both of them up, and you see it does better, it's like, okay, well, was it because of this one or was it because of this one? And similarly, vice versa. But even with rank 1, like the correlation between like any two like parameters is 0, right? The fact that like you know that this one has gone up by some amount tells us nothing about any other parameter, even if they're like on the same row or column, right? So I think that's like the key intuition for why rank 1 is able to work super well. And also like the fact that like you're basically just trying to search in this like gigantic space. So it's almost better to look at it on like a per parameter level. If you look at this one parameter, does moving it up or moving it down on average help? And then all of the other parameters are kind of like part of this expectation, right? So like if I move it up by like 1 tick versus moving it down by 1 tick, and then we try like all other possible combinations of every other parameter, which one was better, moving up or moving down? And you don't need to have perfect independence for that. We just need decorrelation almost. That's the intuition. Of course, formalizing this in like the theory is like a beast of its own.
Oh yeah, I can imagine. But this is cool. I like it happens with the TRM paper also. Totally different, but like I was at the conference where Alexia was showing her stuff, and somebody asked a similar question about like what's the intuition for why this works like theoretically, and she's like, I don't know. Like this guy is working on it, and somebody in this lab like, yeah, I'm working on it. It's hard. So I like that. Like we're gonna make this work, and then after we're gonna figure out why. And I think it will also inform how to improve it later on. We have a question here from Leo that says, I know at the moment Eggroll doesn't compare to PPO in some RL task. I was wondering if you have considered mimicking a lot of the idea behind PPO into Eggroll to form a PPO like Eggroll, because she's kind of get to a good point, because you did kind of inspire yourself a lot from the GRPO. I think you mentioned it in the paper at some point. Yep. So go ahead. Do you have any answer for this?
Yeah. So this is actually a very active area that we're working on, because we were a little bit underwhelmed by the RL results as well. We were like, okay, yes, we beat OpenES, but OpenES. Like OpenAI's ES paper kind of overclaims and says like, oh yeah, we're better than TRPO and all these other methods. Like, not really. Like if you actually are like honest and try to go through all of this, it's like it sometimes is comparable, but like for a lot of problems, it's very difficult. But I think the way of reframing this is we're not. So a lot of prior work has considered ES as an alternative to RL, but I don't think this is the correct way to think about it. I think that ES is a replacement for backprop. So you can use any loss function and you're optimizing it via ES. So this is an extremely stupid idea, but in principle, you could take the policy gradient and you can optimize for the policy gradient loss function using ES. Like it's really roundabout, and I don't think you'd get anything out of it, really. But in principle, you could do that. Now, a smarter idea, maybe, so there's two ideas that are I would consider smarter, right? One of them is you can use Q-learning. And Q-learning is like as famous, like a lot of instabilities. And I would attribute a lot of them to backprop and the fact that we're trying to do this like stochastic gradient, all this stuff. But you could still do like the Q-learning style update, but instead of doing like the loss with the Bellman, or sorry, with AutoGrad, you can use ES for that loss. So you like roll out a trajectory, and then we use like the Bellman optimality equation to try to optimize a Q function instead of the direct, instead of directly trying to optimize the policy. So that's one option. The other option, which is I would say even more radical, but also makes a lot more sense. Well, I guess to prime it, one of the biggest criticisms of evolution is the fact that it needs a large population size, and like Eggroll almost makes this worse, because we're saying, oh, we can have a gigantic population, right? But if you're trying to like deploy a robot to like learn in the wild, right? Kind of the ideal that a lot of people have of RL is like, oh, you have a single robot who kind of just wanders around. It's called like streaming RL, where like you have this agent that just wanders around the world, collects experience, and learns, right? This does not make sense with evolution directly, unless you have like thousands of robots that are all communicating with each other, which makes sense.
Or a world model running, and then you can. Okay, and this is where you're going.
Exactly. So we can learn a world model using the data. We can also optimize the world model itself using Eggroll, right? So we learn a world model. Now we can do thousands of evaluations in parallel on this world model, in order to like do your own like kind of dream your own, similar to like Dreamer, all these other RL model-based RL works. You just dream your own experiences, and something that could be beneficial is the fact that like it's kind of hard to overfit with evolution, right? Especially relative to policy gradients or like backprop specifically. we might not like have all the issues that typically we have with world models, in which you like overfit to the peculiarities of the world model. Instead, you learn kind of something that generalizes. So these are just like other stuff, but like we think there's a lot of interesting directions to take with like, yes.
This is so cool, man. Like, yeah, you guys are gonna this generation of like ES researcher will just revitalize the whole field. You're right. There's like thousands of stuff that we can go for. There's another observation from Leo. She says, or he says, I have no clue. You could always get a larger effective population size through serialization if you run out of memory. Something akin to gradient accumulation, but for Eggroll. What do you have to say about that?
Yeah, I mean that's true. Yeah, so I think there's this paper about gradient accumulation on. Okay, so let me just first out say I'm like a big hater of gradient accumulation. There's this paper that shows that like gradient accumulation is wasteful and like you should never do it. And I completely agree with it. I believe, I don't want to misattribute this, but I think Jan Kuhn says like, oh, friends don't let friends use like large batch sizes, right? Like, but the funny thing is that evolution seems to be an exception where like you actually do end up getting better. But I do believe that like having more updates is better than having like bigger batch sizes in general. It's just that for evolution and Eggroll, we see that like large batch sizes don't actually hurt, which is very interesting, and we wouldn't expect that. But yeah, basically don't. There's some things you need to tune. You need to tune the atom beta 2 parameter if you want to have small populations or small batch sizes. But yeah, gradient accumulation, like I've never used gradient accumulation. I've always, yeah.
Good. That's a good answer. If we move to the egg pre-training thing, I had a question about like a very dumb question. Like, which of the idea came first, right? Like the egg roll idea or the egg one? Like how did you? I think you said it a bit in the story at the beginning, but like in your mind, is it the algorithm that kind of inform this one or the other one?
Yeah. So Eggroll came first, but I think like with egg, we were trying to show like what's the weirdest thing you could do that you probably couldn't do or like not do it super well with standard gradient, or sorry, with standard autograd. So we're like, okay, we need to have. So first, obviously, so for this one, I need to come up with an acronym, right? And I'm like, okay, we can start with evolve generative. And I'm like, okay, what should the last G stand for? So I was like, GRU. It needs to be a GRU, right? So that's the reason why we're using a nonlinear RNN. I need to have a GRU, right? I was also thinking about like, okay, should I do an LSTM? Should I do RWKV? Should I do something else? I was like, I have to use GRU just for the acronym, right? So that's where egg came from.
This is so good, man! Wow. So if people wonder how like all of the details of the research came about, right? There's a lot of this. Right? There's a lot of like actually if we do this, it will look better.
Yes.
I love that, but this is so good.
Yeah. So like I can see like what's the most arbitrary choices that we could make that still like make sense, right? So like for instance, the removal of all activation functions. So like my advisor, he was like consistently prodding me, like saying, hey, can we just like remove the activation functions now that we're doing evolution? Because like he did this work on like, okay, you can use the floating point imprecision and the fact that at like very small values, like things start breaking down for like floating point. I was like, okay, let's do like one better and let's use int 8 and the fact that like it kind of saturates if you do it properly, right? So it's like, okay, I mean, this is even like a cleaner activation function because it's basically just 10H. But like we don't need to explicitly say I want to do 10H, right? Yeah. Or like any of these other, it's called like hard 10H is like the thing that some machine learning people use, right? And then also like pure integer training, I just wanted to see like, int 8. And also like there's a lot of accelerators that are optimized for integer performance, right? And like floating point is super silicon inefficient, so like we could create like hardware that's like designed to do like that can run on like embedded devices, very low wattage, to just do like integer training, right? Because most of these integer only systems, like the Grok with the Q chips, right? They have like super fast int performance and only for inference, right? And there's a bunch of companies that are only doing like high performance a training, or sorry, high performance inference, right? But if they can do LoRA inference, then Eggroll means that they can do training, right? So now we just unlocked like any hardware company that's done anything with LLMs can now like compete with NVIDIA to do.
Jesus, man, this is so fucking interesting. Do you, just random question here. Do you think you can scale the pre-train? Is there any plan to scale the pre-training and see what's up at like in these higher parameter regime?
Yeah. So we're definitely trying to scale both in terms of population size and parameter count. We're trying to understand like what is going on with this model, right? Like we know basically nothing in terms of like nobody's tried to do evolution at like the pre-training scale, right? So like there's a lot to learn. We're seeing that like different optimizers might help. Trying to integrate Atom. Again, Dimitri has done a lot of cool work. He got int8 transformers to work, and it's actually like I would say like almost competitive with like pure SGD on like the NWiki data set. Like it's even better than the results that we've reported on the paper so far. Like he incorporated Atom and stuff like that. So we're also trying to merge that back into the egg model, because like I'm a transformer hater. I want to see transformer rise up. But yeah, so like there's a lot. We're also doing like external memory modules, because like you can just do that. Like it's a super simple inference time thing, but it would be a pain for like pre-training. It's also possible with RL, but like RL at the pre-training level it's a whole other issue, and like people haven't like this is almost like the cleaner direction to take if you want like, reasoning or like I think maybe we will get to this later on, but like there's a lot of stuff we can do at the pre-training level that just wasn't possible.
But also like I had a question like later on about like the hyperparameter. Like, is it more kind of picky than RL, or like similar, or like with the choice of hyperparameters, or like it's less
I think my answer, I think my answer is going to be very similar to what Yulu gave in his interview, which is that like we spent most of our compute budget trying to do hyperparameters for RL.
Jesus, man.
Like it's super stable. And like as long as you understand like what's the general hyperparameter range, it's basically just sigma and learning rate that you need to tune. And like learning rate, it's almost interpretable in terms of how we did it. Like we set up the learning rate such that like you can basically specify like what proportion of the sigma you want to like kind of move over by. So it's like it's quite like smooth and interpretable. And if like things start working, then like it starts working. And if things aren't working, then it's likely, I mean, there's like a couple of like, there's a very small hyperparameter range you'd want to test out anyways. So it's like a very simple sweep that I'd recommend anybody to do. But also like, beyond this like hyperparameter sweep, if things don't work out, then it's probably like fitness functions or like some other stuff, or just like scale with the population size, right? There's so many issues that we resolved. We were struggling for a while to get like good GSM8K results. And then at some point we were like, why don't we just use more GPUs? And we used more GPUs, and we were like, okay, we beat RL. Like that's all we needed. We just needed to scale up, and then using the same amount of resources with RL, like we just beat them, because like it's just so much more parallelizable, and we can just like,
I absolutely I don't know, I'm getting more and more like evolution pill right now. I feel like if we like spend like I don't know, like 6 months thinking about it hard enough, you could get some massive breakthrough with like the pre-training, and then it makes also the post-training, the mid-training, all the weird stuff that we're doing in the gymnastic of like the massive model training become much more simpler. Okay, well, this is fucking nice. I also wanted to know, do you think that like because the cool thing with the RNN stuff is it has this motion of like you have the parameters and then stuff happens and then you have the output, right? Which it's nice because what the stuff happens could be arbitrarily long, could be like funky. You don't have to have like necessarily this kind of back propagation to time kind of thing going. Like it's just like whatever happened here and then you get the output. Do you think that like other kind of fringe type of architecture like the CTM the TRM type, like the ones with like the latent kind of reasoning type of stuff, would benefit from using Eggroll?
Yeah, I think absolutely. So we actually had this like kind of master model that we have in mind, which is like, yeah, there's a lot of radical things we can try, but like one idea is like kind of a latent reasoning thing. But not only is it latent reasoning, but you can choose how much compute you allocate for each token at the pre-training level. So the idea is that you have like this forward pass budget. So like each time you read a token, you have like forward pass budget of like, I don't know, however many layers that you would want, like maybe let's say 20. Like every token, every token you read gives you an additional 20 budget, and you start off with some initial budget. And every time you read a token, you can either choose to kind of like to continue iterating on that same thing, or you can choose to move on, right? And all this is just like something you can define as an inference time loop, especially in the context of an RNN. You can just say like, okay, I just want to keep iterating on this, kind of like understand what this token means, or like try to formulate a plan for like how I should construct the next token, right? Because like, for instance, in a math problem, right? Maybe like you say answer colon, and then like I want to come up with the answer. So it's like, okay, wait, you just put me on the spot. Now I need to like think for like however many iterations I need. And then through Eggroll, it will learn how many iterations should I use before I actually move on. And like this is fully like a black box end-to-end system, and it's like super efficient at inference time. And you can also like parallelize this across different things instead of saying, oh, I need to wait for like, oh, like some like the fifth token should always use like 10 times more compute or something like that. You can just choose dynamically as long as like the number of forward passes or like an update step remains consistent. So like, yeah, that's mm,
To to know that like it doesn't know. So if we can just train this and like at a large massive scale on language, then
yeah.
you could technically get something that is gonna be a bit more smart. So and it will just have this kind of thinking budget, but not happening outside, just straight up in the latent space.
Yep.
Um,
Exactly.
Jesus, I love this stuff.
Can you tell me,
So
like yeah, like how many iterations did they do? Like um for like how many times did they, or like I guess it doesn't really matter like how much they exactly did, but
I
like
think like they went to 100 iteration for the
mm,
images, but like the more they did, the better it was.
mm,
Yeah. Sorry guys, I messed up the sound for 2 seconds. I was just like raving about CTM. I've talked about this stuff enough.
okay.
In general, I love this architecture. I have no clue why. I think it's one of the only one that I've seen which is actually very much brain inspired, but in a useful way, right? All the other ones that I've seen is like it's cool, but it's like the brain algae are not that interesting. Anyway, I just like the
If you want to take the
like
brain like one step further, right? Um, Another idea that I was having, right, is we can do mixture of experts, right? Um, Alongside the CTM. So instead of having like a super deep model with like 80 layers, and all of them are like maybe like a dense thing, you could like with the thing that I was proposing, kind of flatten it out into like a single gigantic mixture of experts layer, and then each token or like the model learns which token, like which layer do I want to. So like in principle, you could go to like the first layer and you realize, oh, I need to think more, I'll go to the second layer.
oh
Or
man.
you could kind of say like, okay, I got it, I'll skip to the end. Or you can say, okay, I still don't understand, let me go back to the beginning and go again. So like with this mixture of experts, now you can have this like thing that kind of cycles around and chooses
Yeah.
like layer of the network it wants to go into, and just exit at any time and just move on. So there's a lot we can do.
There's a lot of stuff to do, man. There's so many cool experiment. Okay, if we move on to the RL task, there's a part that I found very interesting. It says, given the small network size, we can use OpenES at the scale, but we know that as network size increase, the use of vanilla OpenES become impossible. Can you just like, is it because it's not optimized for that, and it's like it's not going to work at larger scales?
Yeah, so I guess for these RL experiments, like RL experiments, what we were doing was we tried to find, we tried to like reproduce existing results from OpenES and kind of just do the same stuff. So like naturally, like by existence, we have to follow the configurations that OpenES works in, right? So this actually limited our experiments to some extent. We were like, okay, we could have a gigantic population size, we could have a gigantic model, but like OpenES, like we wouldn't have a fair baseline against that. So like whether we call it fair or not, we just want to have something that we could standardize against. But yeah, so the issue is that like with OpenES, it's the same batch matrix multiplication issue. If you have a gigantic network for OpenES, it'll just be very inefficient because it scales basically like quadratically, roughly, in terms of compute, versus linearly in terms of like additional compute. So like that's kind of the trade-off that you need to make, and like OpenES completely fails. So yeah, but at these small network sizes, it's not. So like the difference between Eggroll and OpenES continues to become like wider and wider as you have a larger population size and as you have a larger network size. So like the headline chart of like almost like 100 times faster, right? That's with like a large, like basically with an LLM style model, right? So at much smaller models like 256 DIMMs or like even smaller, that's typically used in RL. We still see an improvement, but it's not like as dramatic as like 100x.
Cool. Yeah, that's what I was saying. Like, I think I don't know. I feel like the more you scale, the more you kind of see organically the dynamic of the system much better. Like a dynamic of the problem much better. You guys need more compute. Like you just need to be gifted more.
Yeah, if anybody's listening and wants to give compute, we're like. Jacob has always said this is the most talent dense place. You give us 400,000 GPU hours for like 3 months, and we're able to come up with that growth. So like,
I love it, man.
Collaborations
and another question for the RL task. Like, I see that in this task it was not step size; it was like the wall clock time. So how does it work? Is the Eggroll running more steps than OpenES? Like, what's the flow here?
So I think for the RL experiments, it was steps, so they're the same. The wall clock time is a little bit different because it's kind of hard to compare apples to apples here because we're trying to end at episode terminations, but better models sometimes take longer to finish an episode, so that's why it takes longer to update. Sometimes it's better to finish quickly, so it's kind of incomparable in that context. But for the LLM RL stuff, which I think is what you're referring to in terms of wall clock time. We actually have the same, so yes, we control by the same wall clock time, and we have the same number of steps. So we control
from. Yeah, this is exactly it's the relative wall clock time.
Yeah. So we use the same wall clock time and we use the same number of steps, but we reduce the batch size of GRPO so that each step takes the same amount of time.
Right.
We also did do some experiments where we increased the GRPO batch size, but we see that it actually looks even worse for GRPO. So we're like, okay, let's stick with a reasonable thing that people actually would use in practice for GRPO, and then match how Eggroll would do like in that kind of head-to-head setting to try to be as fair as possible. Because like we could have like GRPO, we have like 32 or like 256 parallel generations in total, which is a decent amount, but it's kind of reasonable for GSM-8K for a 7B model. So yeah, so like we stick with that. If we try to do like more in parallel, it would just slow us down, or it would just slow GRPO down without giving like any measurable benefits from what we saw. So we're trying to be the most favorable we could with GRPO and just like expand Eggroll as far as we could to make it fair.
Do you plan on fine tuning for the LM stuff? Do you plan to like try to fine tune more like mainstream model to be able to have like some sort of benchmark like this?
Yeah. So in our appendix, we actually compared the countdown task for the 7B RWKB model, and we see that we actually outperform all the results in the other paper, which is quite neat because we're better than Quen. And we also start worse. We start worse, but then Eggroll makes it better than Quen. But of course, that's not like a direct comparison. Yeah, so it is we are actively working on getting transformers to work. We're working directly with NVIDIA to help out for like VLM and also what do you call it, the Megatron, and try to get it working with their system. But you know, transformers are just like, I don't think most people realize how bad they have it when they're working with transformers. Like for instance, my prior work, I used RWKV to solve Among Us basically. So I did like, it's like social deduction, training language models for social deduction with multi-agent RL. So this is the first like multi-agent RL for LLMs paper in like an actual embodied setting and stuff like that. And I used RWKV, wrote my own custom CUDA kernels because, you know, RL, we need to have these CUDA kernels to get it to work. And yeah, got all of that to work, but it was still like super smooth. If I tried to do it with like, with transformers, the issue is that transformers take up so much memory because of the KV cap, right? You can't do this like gigantic parallelization. So like you're basically limited by how good batch inference is. So yes, we are working on the results, and we will, in the next iteration of Eggroll, we are hoping to get results for like 100 billion parameter models.
Okay, and Jesus. Whoa.
Like, because this is like almost trivial. So, okay. The issue is that VLM has this like weird caching thing that just like ruining us. Like we're having like the good throughput, we're having everything that we're expecting. Like we just need to go down into the internals and just like fix it so that it actually works for Eggroll, and then we're smooth sailing. Like it should be as fast as batch inference, and it is, but VLM is weird and transformers are weird. And
because I think like if you can like show some clear signal that like this is a direction with these gigantic model and here's how we do it, I think like for sure like the field will pick up pace at this front, because that now it's like, yeah, like it worked here, and now it's even bigger and it's even better, and then we can reproduce that. I don't know, I feel like it's like the last little push.
Yes.
And then people were like, okay, evolution strategy and next NeurIPS is like front and center. You're pretty sure about that. So we have a whole bunch of other questions that popped up. Okay, though, so we have a few things. This one I'm gonna talk about it. One question that is kind of interesting, and then I'll go into more general stuff after that, is what are the bottleneck? This is Mahmoud that said that. What are the bottleneck for ES in regard to GPU computational efficiency?
Yeah. So it's a bit subtle, right? So I would say Eggroll specifically. If you pre-generate the LoRA matrices, it's basically the same thing as batched LoRA inference, right? So like you basically don't see as many bottlenecks. It's basically just the bottlenecks that you would get from just doing regular inference. But with ES, it's a bit weird, like OpenES, like the standard full Gaussian matrix. It's a bit weird because like, strictly speaking, the amount of like matrix multiply flops that you need is less than Eggroll. In fact, it should be the same as you would get from regular batch inference. Yet we still see that's like more than 100 times slower. So what gives? The issue is the arithmetic. Like just the amount of compute you allocate for each byte, right? So it's basically memory bottlenecked, but it's not RAM to VRAM. It's specifically like the VRAM high bandwidth memory to registers, and also like even like within the registers, like all of this additional memory movement that needs to happen. Because like the way the tensor cores work, the reason why tensor cores are so efficient is because we reuse the same matrix and we just like do it on like a bunch of vectors at the same time, right? With batch matrix multiplication that we would have from ES, we would have to like we'd have to do this once and then immediately swap out. So now we're not able to use any of the tensor cores at all. There are some workarounds, right? So I was kind of surprised that the other ES work, they said they have a really small population size, and I'm like, okay, that makes sense. Yes, you would need a small population size, but it's still extremely inefficient, right? So the way that they worked around this is by having a large kind of batch size per population. So while we have like a small batch size per population, so like for each population member, we roll it out like at most a dozen times just to get like a good fitness signal. What they do is they have like a huge, like I think like hundreds or thousands of like evaluations of like the same set of problems across all the different perturbations, I guess. So each perturbation, you actually roll it out 1,000 times. And now you're able to saturate the GPU because you're saying, okay, I have this one perturbation. I want to do just regular batch matrix stuff. But this means that you cannot have a large, this means you can't have a large population size because it will just be linearly increasing in time. So Eggroll allows us to trade off between how accurate do we want an individual perturbation's fitness to be versus how many different perturbations do we want to have. And in a lot of cases, we would rather have as many perturbations as we want and have a very noisy fitness versus like kind of being restricted to having a very large number of like a very accurate fitness just to increase GPU utilization.
That makes a lot of sense. Okay, we're literally massively over time. Sorry for that. But I have a few more questions. Yeah. What will be the next step, like concretely? I know that your lab is like exploring a few things for building upon an Eggroll right now.
Yeah, so there's a lot. I would actually say that the released paper of Eggroll is actually the halfway checkpoint of what we have. We have a lot of things planned. We're improving RL. We're trying to like scale up the RL results, do the Q-learning stuff, world models, UED. Like there's a bunch of stuff that our lab has been working on, and we're just seeing like, can we Eggroll it? How does it work? Just so that people can have like more data points in terms of like, okay, does this work for my situation or not? So there's like a lot of stuff where we're trying to like build on like prior work. But then there's also a lot of new and interesting things that we can try out. So I'm super interested in neurosymbolic AI, or like trying to add some new structures to this. So like one idea that we mentioned in the paper is like, or I guess in like the blog posts and other stuff is, so RWKV8 has this like ROSA mechanism, which is like basically like a discrete memory system that kind of means that you don't need to do self-attention anymore. You instead create your own discrete sequence. It's a bit complicated to explain like very briefly, but you can think of it as like an alternative memory mechanism that you can just index into. And yeah, this would be like something that we can just very easily integrate. Whereas like the current things that the RWKV community is using is like a straight through estimator, which is just like trying to fit autograd into this thing that autograd doesn't fit into. So we want to see like, can evolution release this issue? The other thing is like, we can add like compute inside. So like we could have a Turing machine that's actually directly connected to our, like that's used within the loop of our model to do like external computation and stuff like that. And kind of just like have a regular RNN that can also have this like scratch pad or like whatever you want, and stuff like that. So yeah, there's a lot of stuff that we're testing out, and also like scaling up pre-training, and yeah, just seeing how far we can take it. There's a lot of stuff that we're just like trying, and we're like, oh, it works. And like, should we add this to the paper or not? Like, we don't want it to be like too overwhelming because it's like
the paper will be like 200 pages long.
Yeah, our appendix is going to be insane. But yeah, we're trying to find like what are the most interesting things that like people find relevant. So yeah, like if anybody has like interesting stuff that they would like to see for like a full version of Eggroll, please like let us know. If you'd like to try out, there's a bunch of people who've already, like the community has already gone insane in terms of like implementing stuff. Someone has gotten text to image fine tuning to work.
Oh wow!
In PyTorch, right? Using LoRA or using Eggroll, I guess. And the results look pretty good. I'm not super into like image stuff, so I'm not like too well versed about like what's good or what's not. But like compared to the baseline, it looks really good. And yeah, so there's a lot of I'm really excited to see where we can take this.
There's a guy in the chat that asked, "What's the simplest way I can get started on ES? Like, what's the path? Do you have any like favorite starting point here?"
Yeah. So I would recommend Lillian Wang's blog post on ES. Like, if you just search up like evolution strategies, it's a really good starting point on like understanding like what evolution strategies is. I think like it's a very good starting point. There are a couple of things that I would correct, but like I think overall it's a very excellent resource. So that's one thing. I will also be releasing like shortly, like for Christmas, I guess, like a small Jupyter notebook that you can run on any system about like
nice.
with Eggroll, you just run through everything. You don't need to install anything other than JAX. and you can run it on like CPU, GPU, TPU, and you just train like a very simple function, like function approximator. And then you can take this and then like do whatever you want. And yeah, and then also just looking at the Eggroll repo, we have some examples that you can work through, especially for like LLM fine tuning. You can just get started by just running it immediately using the GPU. In fact, a lot of our original experiments with Eggroll started with a single RTX 3080 to fine tune like a 0.1B RWKV model, and that's where we found our first sign of life. So like this works at like the small scales of like a single 3080 GPU. It can go down even lower, like a 2080 or something, and it can go up as like basically thousands of H100s is where some of our biggest experiments are currently. But yeah, there's a lot. It's for everybody, right?
Cool, man. This is so interesting. Thank you very much for taking like an hour and 30 minutes to just come here and chat with us about that. People, if you want to reach out to him, check out his Twitter handle. It's in the description of the video. Do read the paper, right? It's a really good paper. Take your time for it. Bidipta, thank you very much. And as soon as you have an update, just ping me. I wanna read it.
Yes, definitely will do. Thank you for having me.
Fantastic. See you, man.
All right. See you.
That was awesome, man. Like, wow. Jesus. I'm fully I don't know how to say, like, I'm fully evolution strategy pilled right now. I think there's something there. Like, to be honest, I think as soon as like this lab or another lab are gonna crack a bit, like the whole gigantic parameter size angle, and if they get enough GPUs to do that, and work around like the little like internal GPU problems, I think like it has the nice properties of that are kind of circumventing some of the weird stuff we're doing right now. Anyway, so do read the paper, folks. I think this one is a good one. Do read also the other ones. I think it's gonna pan out to something big. And do follow Bidipta on Twitter. Guy is super smart. And yeah, it's the whole lab. I think we'll see great stuff from them. Fantastic, folks. Have a good one, and we'll see each other next week.